In the previous class, we were looking at the forced oscillations or vibrations in a series LCR circuit, and we were discussing about how the circuit brings the concept of resonance into picture. Okay, so let's just recall what we had done and then we will proceed. So we consider a series LCR circuit connected to a AC power supply. So the value of inductance is L, the value of capacitance is C, and the value of inductance is L. Inductance is L, capacitance C, R is the resistance. So let us assume that the voltage across inductor is VL, voltage across capacitor is VC, and voltage across the resistor is VR. Let the power supply be V and the current flowing in the circuit is I. So since we are expecting a power supply voltage to be sinusoidal, so we assume that V is equal to V naught into sine of PT. That's what we call as equation number 1. Then we assign the equations corresponding to each of the uh, inductor, capacitor and resistor, like Vc is equal to Q by C, charge by capacitance. VL is equal to L into di by dt. L is inductance, I is current, but I itself is a derivative of charge. So because of that reason, L into d square Q by dt square is the equation for the voltage across inductor. So that's equation 3, and VR is equal to I into R. I is dq by dt, so we have equation 4 saying that VR is equal to R into dq by dt. So that's equation number 4. Then we apply KVL to the circuit in the direction as shown in the circuit diagram. So it marks that we are moving from in the clockwise direction in that circuit. So it means that we are applying in the following fashion, right? The KVL says that algebraic sum of voltages equal to 0. That's why. So we are starting from plus of the power supply. So it is plus V. Then plus to minus is minus of VL minus VC minus VR equal to 0. And after that we take the negative terms to the other side. So that gives an equation like VL plus VC plus VR equals to 0. So now we substitute the values from the previous equation. L into d square Q by dt square plus R dq by dt, Q by C is equal to V naught sine PT. So we divide the equation by L so that the first term becomes only d square Q by dt square plus R by L dq by dt, and the next term becomes Q by LC, which is equal to V naught by L into sine PT. This is the equation given with the number 5, which is the governing equation for an electric circuit when it has a series connection of R, L and C. At the same time, if you check the original equation that we wrote for any mechanical or physical vibrating system, that looks like d square y by dt square R by m dy by dt plus mu by m into y is equal to f by m into sine of pt. So now we should be able to compare the equation number 5 and equation number 6 so that we get the correspondence between the quantities of mechanical and electrical oscillators, right? So we can write here, therefore comparison of 5 and 6 gives the correspondence between mechanical or the physical and the electrical oscillators. Okay, from equation 5 and 6, we can see that in the first equation we have d square q by dt square, and the second term has d square L by d. So let's try to highlight with the colors, saying that what are equal. So there is a q over there is a y here. So q and y are equivalent. They're not same, they're equivalent. So q is charge, y is a displacement. So displacement and charge are analogous to each other. So whatever is the position taken by the displacement in a mechanical operator, same position is right handled by the charge of an electrical oscillator. Okay, very similar to that. Then the next term is, say, this R. So the capital R is a resistance and the small r is like a damping factor. So they are also equal. Then the L value in equation 5, right? The L value in the equation 5 is very similar to the mass of a mechanical or this thing. So you can see that. Then let's use other colors to identify. Anyway, Q is done. T remains same as T. So then we have Q and Y are marked. Let's say that L and M are equal. That's also already has been marked. Then we have the capacitance C and the mu. So the C is in the denominator. Over here you can see C, and the similar position is held by the mu over there. This is because you can see M already we have equated. So L and M are equal. The Q and Y are equal. That's why we cannot equate any other terms. We have to equate. Then the V naught. You can see that there is a V naught equation in 5. That is very similar to the F in this equation. Okay, so other than that, both the equations will remain very much similar. Okay, now we'll whatever we mark just now, we'll try to write it in the form of a table. Okay, so on the left side, I'm going to write the points corresponding to the mechanical system, and on the right side, let me write about the electrical system. Okay, so on the left hand side, I'm writing the quantities of mechanical oscillator, and on the right side we are writing electrical or electronic oscillator. Okay, the first thing to equate is displacement, that is y, and this is actually equivalent to the charge denoted by q. Okay, and the second quantity which we can say they are equivalent is So on the left hand side, in a mechanical system, this is the mass of an object denoted by m, and equivalently on the other side, this is inductance capital M. Then we have this is velocity, that is v is equal to dy by dt, right? We can see that this is equivalent to current. So this is denoted by I, which is equal to y. We have q here, so this becomes dq by dt. Then we have what is called as a damping factor, denoted by small letter r. So this is equivalent to the resistance. Resistance is denoted by capital R in among those equations. Then after resistance, we have what is called as a force constant. So you can see that this force constant denoted by mu is equal to, right, is 1 divided by, it's a capacitance. Okay, now after this capacitance, that is 1 by C, we have the last term coming up, which is maximum so this is maximum force denoted by capital F. It is equivalent on the other side to the maximum voltage. Okay, this is maximum voltage, that is V naught. So since we know the equivalence of the mechanical terms with the electrical terms, now what we can do, we can go ahead and calculate the relations between the omega and V, etc. So now you see we know something, so let's apply whatever we know and proceed with the derivation. So here So we know that omega square is equal to 1 by LC. Okay, and also we have already used a property, that is R by M is, it should be equal to capital R divided by L. This is equal to 2 into B. Okay, so what is the natural frequency? But the natural frequency should be equal to omega by 2 pi. Right. Now, so since omega square is equal to LC, this implies now I can write omega is 1 by root of LC. So omega is nothing but 2 pi f critical, right? Or okay, let's write just f as of now. So first let's find the value of f. So this omega is what? Omega is equal to 2 pi f. This should be equal to 1 divided by root of L into C. So this implies the frequency of operation of that object is nothing but 1 divided by, this will be 2 pi. Okay, so we have 1 divided by 2 pi into root of L into C is the natural frequency of oscillations of a LCR circuit. But now we also need to calculate what is called as a quality factor. So Q is equal to, this is omega by 2 times B. So omega by 2B. So B is equal to R by L here, and omega is 1 by root LC. So this implies the Q is equal to 1 by root of LC into the 2B should be R by M. Now the root L is going to cancel with L as root L and R in the denominator. So that means I can write Q is equal to, so this L cancels with L as root L. So this becomes the R in the denominator and 1 L will go to the numerator. So 1 by R into root L by C is the quality factor of the expected circuit. So then we move on to the calculation of the capital A and the maximum amount of charge stored in this device. Okay, now, so therefore the amplitude of vibrating system in a forced oscillation this should be equal to, we know that the standard equation is F divided by under root omega square minus I think it is a p square, sorry, omega square minus p square the whole square plus this is 4b square into p square. Okay, so the f is nothing but capital F by m whole divided by this is square root of omega square minus p square the whole square plus 4b square into p square. So now we need to substitute the value of f as capital F by m over here. So once we do that, we get the equation of A as like this. Now corresponding equation. So we can write the equivalent equation of the electric oscillations, right? So therefore we write the corresponding quantity in LCR circuit, right? When we write the maximum voltage, maximum amplitude of an oscillation, its equivalent is maximum charge, is the maximum charge. So maximum charge, let us call that as Q naught. So Q naught is equal to equivalent term, let me write. So F is nothing but V naught. M is nothing but L. So V naught by L whole divided by square root of, I can see that omega is nothing but 1 by LC. Okay, this is omega square. Omega is 1 by root LC. Since I am squaring, it's 1 by LC. A minus P remains as it is, so P square whole power 2 plus, so 4B square is nothing but 2B whole square, but I know that 2B is nothing but R by L. So it's a square into P square. Okay, so we substitute this. Now we know that there is a value called the inductive reactance, which is P into L. Right? Whenever you see that there is a inductor offers certain amount of resistance to the flow of current, and that value is what is called as the inductive reactance. Okay, so let us try to write that now. So, but the inductive reactance XL is equal to the P into L, and also we can write the capacitive reactance, that is XC, which can be given by 1 divided by P times C. Okay, now if you see, we try to divide one by the other. Therefore, XC by XL is nothing but XC is what? XC is equal to 1 by PC into XL. When it goes to denominator, it is 1 divided by P into L. Right? So XC by XL is 1 divided by PC into 1 divided by PL. So what I am trying to do here, I'll keep the LC on one side, take the P and P into P is P square. So I can write here itself, this is P square LC is XC by XL. So this implies if I want to write 1 by LC on one side, this should mean that P square goes to the other side into XC by XL. Right? We know this thing. So also we know the R by L, the whole square, is equal to, we can try to write this L as XL by P square. Okay, XL by P square is nothing but the L. So we'll try to write it in the same notation. Therefore, this is equal to R divided by, this is XL by P square, this term, the whole square, which can be reduced now to capital R square into P square divided by XL square. Right, now all these values, let us substitute back in the previous equation. So this implies the value of Q naught can be, so just see what we had substituted, whatever we got earlier. So we'll substitute everything back. This is first term, numerator is V naught by L, and in the denominator we had the omega square, so that can be replaced by P square XC, P square into XC by XL minus P square whole square. First term, sorry, there is a square root, there is a square root, okay, root of this term whole square plus the next term is R square P square divided by XL square into P square. Okay, so what we are trying to do now is that I can see that the XC by XL, right, that XL and P are common from in the denominator, so we can take that term out. Okay, so V naught divided by L can be written as, so that I'll make a change in the numerator. So this is also equal to, I'll keep the V naught as it is. The 1 by L is nothing but P by XL whole divided by, so in the denominator, let's try to take out the common terms. So I can see that there is a P to the power 4, right, into this XC minus XL divided by XL, the whole square. This is what is the resultant of first term. You can see that P square common, but there is a square, so when it goes out it becomes P to the power 4. Then plus, this is R square P to the power 4 divided by XL square. So I can see that the XL square is also common in addition to the P to the power 4. So let's write, this is V naught into P by XL whole divided by, so P to the power 4 is common in both the terms of the denominator, so it will go out. When it goes out, it becomes P to the power 2 divided by, see the denominator has XL square, when goes out of the square root it simply becomes XL. Okay, then into square root of, this is XC minus XL the whole square plus, see P also gone out, XL also gone out, we just have R square. So this is equal to, on the left hand side let me write the term which I have, right? So let me cancel the terms. 1P cancels with the term, XL cancels with XL. So we are left with the following term. So left hand side is Q naught. Q naught is equal to, there is a V naught divided by, right, you can see there is a P left over into square root of, this is XL minus XC the whole square, I think XC minus XL. Let me write this in the same way. So this is XC minus XL the whole square plus R square. So this means, let me take the P to the other side. Therefore, P into Q naught is equal to V naught divided by, this is under root R square plus XC minus XL the whole square. But P into Q naught, right, is nothing but the peak value of current. So this is the this is all together. Okay, P into Q naught is the peak value. So this is called as the peak value of current. Right. So peak value of current, let us denote that as I naught. I naught is equal to the V naught divided by square root of, this is R square plus XC minus XL the whole square. Right. This actually I should be able to equate with V naught divided by magnitude of Z. So here the Z is called as the impedance. Right. So this implies I can actually find the magnitude of Z as the denominator itself, that is R squared plus this is XC minus XL the whole square. All right, now we come to the last theory point of this particular topic, that is the resonance in LCR circuit. So we know that when the frequency of applied signal becomes equal to the natural frequency of the circuit, we can say that the given circuit is in resonance. So this implies, let's try to write the condition now. So when the frequency of the applied AC signal, in the sense the power supply, becomes equal to the natural frequency then the series LCR circuit is said to be in electrical resonance. So the point is that at resonance the P becomes equal to omega, right? So we'll write that, therefore at the resonance the input frequency P becomes equal to omega, which is the natural frequency of the circuit, right? This is, say, equation 1. But for a given LCR circuit, right, for LCR circuit, the omega is actually equal to 1 divided by root of LC. So call this equation number 2. Okay, now so we know the equation of P, which is equal to omega, right? So equating 1 and 2, 1 equals to 2, this implies now the P becomes equal to 1 divided by square root of, right, we have to write the value of what do you call, the L is nothing but, if you remember, this is XL by P. Okay, and the value of C can be written as 1 divided by P times XC, right? So you can see that this can be simplified as 1 divided by square root of, there is 1 by P square into, this is XL by XC. This means that 1 divided by, there is 1 by P times root of XL by XC, right? This is, on the left hand side I still have P, so P becomes equal to, the 1 by P in the denominator goes to the numerator as P divided by root of XL by XC. I know that this cancels, so it is left with 1 on the left hand side. So this implies, if you take the square root of XL by XC to the numerator, you get 1. So squaring both sides, the XL by XC is 1 itself, so this implies XL is equal to XC. This is one condition for resonance in the LCR circuit, right? This is the required condition of resonance in LCR circuit. Okay, so when this XL becomes equal to XC, therefore if XL is equal to XC, right, which means corresponding the Z is minimum. This implies, now let's write the current, that becomes maximum current because resistance or the impedance becomes minimum. So this is nothing but V0 divided by root of R square plus 0, because this 0 is XL square minus XC square, and XL and XC are same. So XL minus XC means they are 0 because they are same. R square remains as it is. So the whole term in the denominator becomes R square plus some constant C. So normal calculations, the constant is always made 0. Okay, so this is the condition. So this implies, now let us write the maximum value of current becomes simply V0 by R. So the effect of the XL, that is impedance, and also the effect of the XC0, which is nothing but the capacitive reactance. So both the terms we had written here, but the total answer can be simply found by neglecting XL and XC, and we can definitely use the maximum value of the current can be found simply by using the applied voltage V0 and the resistance R. So inductance and the capacitance have no control over the required Imax. Okay, so I think that finishes the theory concepts of this chapter.